Okay, so as promised, I will display my new slides, new chapters. Okay, hopefully you can have my notes in my future. Okay, in my future, you can all the notes are there. So please download it. Okay. Okay, the new topic will be the after the magnetism, after we learn about magnetisms. Okay, so as usual, I want to do a quick recap on the magnetism, which we in the magnetism we learn about the properties of the magnetic behavior. Okay, all about magnetic. Okay, and we also learn about how can we get a magnetic force. Okay, from the moving charge, and another one is the magnetic force from the current carrying wire. So there are two magnetic force. Okay, but from that particular equations, we can get magnetic field. Okay, magnetic field B. Okay, what is magnetic field? So we can derive a lot of magnetic fields equations in the magnetism. So for example, we can have B equals to F over QV for the moving charge. B also equals to F over IL for the current carrying wire. And we learned about Ampere's law. Okay, B equals to mu naught I over 2 pi R. Right? Okay, and then we also learn about how to get the magnetic fields come up from the solenoid. Okay, from the solenoid, that means we can have B equals to mu naught n, small letter n times I. Okay, small letter n times I, which means small letter n is n, yes, capital letter N over I. Okay, capital letter N over, sorry, over L. N over L, number of turns per unit length. Okay, so another one is we also learn about torque. Okay, torque in the magnetism, which we have NIAB sine theta, and I and number of loop, I current, A is the area, and also B is the magnetic fields. Okay, and we also learn about how can we get a force between two current carrying wires, two parallel current carrying wires. Okay, either is going or the current is going on the same direction or opposite direction. So on the same for the current having in the same directions, okay, it will be a repulsive, it will be a attractive force. But for the current that having a opposite directions, so it will be a repulsive force. Okay, so there are certain things that we should learn a little bit in the magnetisms, which we have to uh, uh, deal with some things that related to magnitude and directions. So the equation will give you, the equation will always give a magnitude. Okay, but from our right hand rule, okay, a lot of rules, okay, we can have in the magnetism, which we can learn using the right hand rule. Okay, a simple right hand rule. Okay, for the positive charge, and for the electron we'll use the answers that's against the right hand rule. Simple. Okay, now maybe you can use the left hand rule. Okay. Okay, so right now we want to learn the new topics about magnetic flux and the Faraday's laws of induction. So what is magnetic flux? Okay, before this we learned about magnetic force, magnetic fields, and now is magnetic flux. Okay, all right. So let's take a look at what is the magnetic flux. All right. So these are the learning outcomes of this topic, and these are the units of chapters. Right? So we will learn the electromotive force, the induced EMF. So this induced EMF. Okay, the magnetic flux. So here then we can learn magnetic flux. And okay, so what is the purpose of learning a magnetic flux, and what is the Faraday's laws of inductions? Okay, laws of induction. And what is the Lenz's law? Okay, good law to understand the Faraday's laws of induction. Okay, mechanical work and energy, the generators and motors. So these are the applications. Okay, applications of Faraday's law. Okay, Faraday's laws. And lastly, we will learn about energy storing in the magnetic fields, and also the transformers. Okay, the transformers. Okay, so first of all, this is the induced EMF. So what is induced EMF all about? Right. So when we talk about induced EMF, you should learn from this experiment. Okay, we call that as the Faraday's experiment. Right. So what is Faraday's experiment? Okay, it is saying that we can have two circuits. Okay, two circuits, which we have primary. Okay, this is the primary circuits, and another one is secondary circuits. Now look at the primary circuits. Okay, in the primary circuits, we will have a switch. Okay, this is switch, right? Then we can have a, a, a battery, and another one is resistance. Resistor. Okay, and also we will have some sort like uh, current carrying wire, or should we call it as solenoid. Okay, we learned before this about solenoid. Okay, a series of the number of wire, okay, that have that will experience a magnetic field. Okay, and then this is the iron core. Iron core. Okay, so another one is the secondary circuit. In the secondary circuit, we'll have a solenoid or a series of wires, okay, and a galvanometer. So these are the several uh, apparatus and components in the electrical circuit that should explain what is the Faraday's law, or what is the induced EMF all about. Okay, so what is Faraday's experiment? So it's saying that closing the switch in the primary circuit, so look at the words, closing the switch in the primary circuit induce a current in the secondary circuit, but only while the current in the primary circuit is changing. Okay, so what is the words is telling you now? Okay, so Faraday's laws of experiment is using primary circuit and secondary circuit. So what happened is, okay, it's saying that when you close the switch, okay, you close the switch in the primary circuit. You close means that you, you close the switch. Okay, that means the circuit now is closed, so it can transfer the current. Okay, the current will be transferred from the battery. The current will be transferred, and then the current will go to the solenoid part. And what happens is, when you have a current carrying wire, so you are actually generating the magnetic. So this is magnetic fields, okay, occurs in the iron core. Okay, in the current actually, magnetic fields occur in the current, in the current carrying wire here. Okay, in here. So right now, uh, you can see that, okay, in the secondary circuit there are no battery, there are no supply of power supply or batteries in the secondary circuit. So that is not possible to have a current in the secondary circuit at once. But according to the Faraday's experiment, we can have a current in the secondary circuit, okay, without having any power supply or battery. Okay, but you must connect the secondary circuit to the iron core, which is here. Connect the circuit of the iron, connect the secondary circuits to the iron core, and then you can have the galvanometer. Remember, galvanometer will have a needle, okay, in the middle. Okay, zero. So galvanometer will shows that it will changing from here to here. Okay, it will change the directions. Okay, because the functions of galvanometer is not to measure the current, but um, to detect the current. Yes, to detect the current, but not to measure the current. So if we want to measure the current, we use ammeter, but the galvanometer is just to detect. Is there a current in the secondary circuit? Yes. So that's why we are using galvanometer, and because of the needle is in the middle. So it can show us that where is the directions of the current. Right? Yeah, either is from positive to negative, or negative to positive. So what the Faraday's laws of Faraday's experiment is telling you is when we have current. Okay, we have a power supply in the primary circuits, we can transfer the current through a magnetic fields in iron core, and then it generates the magnetic field, it generates the induce. That's why they use the words induce, because induce, okay, as we learned in the previous chapter, is not touching. Okay, we cannot touch. Okay, let's say the transferring the charge using induce the, okay, inducing the charge, so we cannot touch. Okay, the touch should be conduct. Okay, conduct, that means touch. Okay, but induce is a just, okay, it comes near, okay, closer to the secondary circuit, and then we can have a current generating from the solenoid and goes to the galvanometer. So for the details of the experiment, then we can show here. When the current in the primary circuit is not changing, okay, it's not changing, therefore the magnetic field in the iron bar or iron core is not changing also. Thus, the current in the secondary circuit is zero. Okay, so what is in the Faraday's experiment, in order to get the secondary circuits current, okay, get the current in the secondary circuits, the switch will play an important role. Why I'm telling you now? Because the switch, okay, must be not in the appropriate way. You must always, okay, change the directions of, change the current. You must always um, make the current change in the primary circuit. So how to make the current change? So if say we are closing the switch, okay, the tutup switch, all right, what happened is tutup means kita close the loop of the circuit. Okay, maksud dia ada current. Okay, you can have current. So you can have current, and then the current will flow. But when the current flow, okay, we can see that there is a deflection in the galvanometer. But and after some time, okay, maybe 1 second after that, it will go to zero back. Okay, it will go back to zero. And afterwards, when we open the switch, okay, we open the circuit, so there are no current inside the primary circuit. Then again, we can have a needles deflection in the galvanometer. So we actually experience or observing some things, okay, related to the switch or related to the current. The current must always change. Okay, current in the primary circuit, in order to have a stable secondary circuits, okay, current in the secondary circuits, you must always, okay, uh close and open, close and open, close and open, do a close and open, and then it will play around, you will play around the current, and the current keep changing from time to time, and the changing of the current in the primary circuit will make the secondary circuit have a stable current. That's why we are saying the secondary circuit will have an induced current. Okay, but when you have no when there are no change in the primary circuit, okay, magnetic field is not changing. When magnetic field is not changing, the current in the secondary circuit will be zero. So let's say if you are, let's say, from closed circuit. Okay, from open circuit to closed circuit. Closed circuit means you have current. Open circuit, that means you have no current. Okay, from closed circuit, sorry, from open circuit to closed circuit. So you will have a current generates from the magnetic fields in the primary circuits, and then you can transfer it to the secondary circuit. So at that time you have current, but when you just leave your primary circuits like that, that means just close the circuit in the primary circuit. Yes, there are current in the primary circuit, yes, but it cannot transfer, because it cannot transfer the magnetic field, because the magnetic, in order to magnetic fields to be transferred from primary circuit to secondary circuit, is you must have to change the current from time to time. You must always make the current change from time to time. So you cannot have a stable current in the primary circuit in order to have an induced current in the secondary circuits. So that is the Faraday's laws experiments telling you. Okay, so the current flows in the secondary circuit while the current in the primary is changing. Now, you must keep change the current in the primary circuit. It flows in opposite directions depending on whether the magnetic field is increasing or decreasing. The magnetic of the induced current and the induced EMF are proportional to the rate at which the magnetic field is changing. So remember, induced EMF proportional to the rate at which magnetic field is changing. Okay, so opening or closing the switch in the primary circuit induce a current in the secondary circuit. So you must get the idea of what is the Faraday's laws experiment telling you now. Okay, so the switch should be open, close, open, close, open, close, in order to have a stable current in the secondary circuit. Because when you have a stable current in the primary circuit, so you cannot have stable current inside the secondary circuit, because everything that happens in the secondary circuit is what we call as induced. And how to get the induced? So you must make sure that the current in first circuit changing. Okay, you must always make the current in the primary circuit change from time to time, change from time to time. Okay, so note the motions of the magnet in each image. So let's say, okay, look at the possibilities of the magnet. We have a magnetic but a bar magnet that have north pole and also south pole in the end. So when the north pole is getting nearer, okay, is getting nearer to the coil, okay, coil of the, this is what we call as coil. So now you can see that there are some deflection of needle. Okay, the deflections of needle in the galvanometers. That means there are some induced current, okay, in the coil. Okay, without having any power supply or batteries in the coil. Okay, but okay, we have a coil, and we straight away, okay, connect it to the galvanometers. Okay, why? Because we want to detect whether there is a current or not. So when we try to bring, okay, look at the arrow here, arrow. Okay, this is how the magnet is going into the possible coil. Okay, remember coil. Okay, have a round coil, so we can get the magnetic field through the coil. So that means there are some changing from zero to magnetic fields, from zero magnetic field to maybe one or two magnetic fields. So it doesn't matter as long as the magnetic field is changing. Okay, magnetic field is changing now from zero. Okay, maybe at start we have zero, and we try to bring the magnet nearer to the coil, and you can see that here, these are the magnetic field lines is getting a lot in the coil. So that's how you can see that the change in the magnetic field lines. from 0. So you can have, so when the magnet is get clear, is get near or closer to the coil, then you can see that the needle is increasing. Okay, but if there are no movement, okay, this is the fun. No movement. Okay, no movement. That means you try to bring the you try to bring the magnetic bar. Okay, but you stop at one moment. You stop. So V equals to 0. That means stop. Okay, it doesn't move. Okay, it doesn't involve any change in the magnetic fields. So you can look here. No deflection. But then again, if you try to bring out the from that position, try to bring out the magnetic bar. So now you can see that there is some deflections of needle, but in the opposite directions. Okay, if at figure A, you can see that the value is quite near to the positive value, but when you pull back the magnetic bar, okay, in the figure C, you can see that the deflections is going to the negative value. So in order for us to get a very stable induced current, so you must make sure that the magnetic bar, which have a magnetic field, must always changing. So like the one that they did in the figure at the bottom, this man, okay, is always change. Okay, masuk keluar. Okay, try to bring out and bring in the magnet into the coil, into the solenoid, because they wants to make the induced current. So this is what we call as induced current. Okay, it's not a normal current, but it is a induced current. Okay, so that's how you can play around with the magnetic bar. Okay, the magnetic bar, you know that, okay, where is the directions of magnetic field doesn't matter, but when you can see the magnetic fields changing, then there will be the induced current. Simple. Okay, when there is a change in magnetic field, there will be a induced current. So from induced current, we can have induced EMF. So what is induced EMF? Induced potential difference. Okay, so induced current can have induced potential difference or induced electromotive force. Okay, so let's look at these examples. Again, not examples, but illustrative figure that's showing that, okay, what happens when we try to bring on the magnetic bar towards the coil. You can see here the magnetic bar, the same as what we did just now. The magnet move up towards the coil. Okay, so look at here, B in coil increasing. B in coil increasing, therefore it will make the deflections of needle become close to the positive value. Okay, and same goes to here. When we try to bring out the magnetic bar, then the B in the coil is decreasing. Okay, why? Because from a lot of B, okay, when we try to pull back, then there are no that it will, the B will decrease. B in the coil, this is coil. Okay, this is coil, is decreasing. Okay, you can see here there are a lot of magnetic field in the coil, but right now the magnetic field is getting, when we try to bring out, okay, it will be decreasing. So that's how you can see that the value will be more to negative. But when there is no movement, that means you bring the magnetic bar and you just hold the magnetic bar. Okay, you doesn't pull back or pull it, you doesn't push in or pull back the magnetic, you just hold the bar like that in the middle of the coil. So there are no movement. That means B in the coil constant, and when B in coil constant, that means the current is not induced, there are no current. Okay, current will be 0. So in order to have a stable current, you need to do a pull back, a push and pull the magnetic into the coil. Okay, because we want to make the B becomes increasing or decreasing. Okay. All right. Any questions so far?
No.
Thank you. Okay, so right now we want to learn about magnetic flux. Okay, as promised, this is magnetic flux. So what is magnetic flux? So in order to get to know the magnetic flux, we should learn about magnetic field. Okay, because magnetic flux is a measure of the number of magnetic fields that cross a given area. Okay, that means in order to get the magnetic flux, you must have a magnetic fields. Okay, and the magnetic flux is used in the calculations of the induced EMF. So we just put aside first the induced current and induced EMF that we learned just now from the Faraday's experiment. But right now we want to learn about the how to calculate the magnetic flux. Okay, the magnetic flux. Okay, magnetic field is B. Okay, this is magnetic field. I hope that right at this moment, okay, you get no confused between what is magnetic field, what is magnetic force, and of course today we want to learn about magnetic flux. Magnetic flux is phi. Okay, the symbol phi is called magnetic flux. What is the difference between magnetic flux and magnetic field? Okay, magnetic field is just a medan magnet. Okay, medan magnet. That means how powerful is the magnet. Okay, so that is the magnetic field. But the magnetic flux is much more um, uh, focusing on the area, because when you want to learn about magnetic flux, it also involves area. What type of area are we talking now? So the definitions of the magnetic flux is BA cos theta. Okay, flux is BA cos theta. BA cos theta. Okay, what is B? B is magnetic field and A is the area. Okay, magnetic field and area, and theta is the angle between what have been going out from the. So let's look at the figure A if we want to learn about theta. Okay, theta in figure A is saying that this theta is 0. Okay, theta will be 0 in figure A. Okay, why? Because the dotted line here, is considered to be magnetic flux, and the blue line here is the magnetic field. This is B and this is phi. So cos theta in the equations of magnetic flux is the angle between flux and the magnetic field. So in this case, when flux and the magnetic field um, is parallel, therefore the theta will be 0. What happened when theta 0? Okay, what happened to theta 0? So if you try to bring this cos 0, remember, will equals to 1. Okay, cos 0 is equals to 1. Cos 90 will equals to 0. So in the second figure, figure B, so this is the flux. This is the flux, and this is B, magnetic field. And the flux and the magnetic field, remember, look at the flux. Okay, let's say you have a loop of wire. Okay, loop of wire, and then of course this is the area. Okay, the area of the loop. Okay, and then flux is 90 degrees from the area of the loop. Therefore, okay, 90 degrees. So theta, its theta to the magnetic field is 90 degrees also, and therefore cos 90 will be equivalent to 0. So in this case, flux maximum, flux 0. Okay, and then this one is flux equals to BA cos theta. Okay, simple. Then you can have a maximum flux. Okay, flux equals to 0, and also flux equals to BA cos theta. And the unit for magnetic flux is called Tesla meter square. Look at the words. Okay, BA, flux is BA. Okay, B is Tesla and A is meter square. Tesla meter square, or equivalent to Weber. WB. Okay, Weber. Okay, the unit for the magnetic field is what? Okay, magnetic field is Tesla. Okay, then the area is meter square, and Tesla meter square is the where is the unit of Weber. Okay, simple. So look at these examples. Consider a circular loop with 2.5 centimeter radius. Okay, circular loop. Okay, 2.5 centimeter radius. So this statement wants you to get the area. What is area? Pi r squared. In the constant magnetic field, so this should be your B. Okay, find the magnetic flux through this loop when its normal makes an angle of 0, 30, 60, and 90 with the directions of the magnetic fields. So like this. Okay, this is 0, this is theta equals to 0, this is theta equals to 0, this is theta equals to 30, this is theta equals to 60, and this one theta equals to 90. Okay, so you need to do it on your own because it's simple. Okay, flux is equivalent to BA cos theta. And what is B? 0.625 pi r squared. Remember to get r in the, before this is 2.5 centimeters. Okay, but you need to change to meters. And cos 0, so you will get the maximum value. And then if you look at the cos 90, so it will be 0. You don't have to calculate because ultimately it will be 0. And if the cos theta is 30, it becomes 1.06, and cos 60 it will be 6.14, much more smaller. Okay. All right. Okay, I try to read the questions. In order to change the magnetic flux here, this is the question. In order to change the magnetic flux through the loop, what would you have to do? Okay, so first one is drop the magnet, move the magnet upward, move the magnet sideways, only A and B, or all of the above. So the answer is all of the above. Okay, so that means when you are actually moving the magnet sideways is here, from here to here, sideways. Okay, so that is also considered as change the magnetic flux. Okay, because when you have a loop, so you are changing the magnetic flux, because we know this is the magnetic fields, but magnetic fields that falls in the area is called magnetic flux. Okay, so please remember what is magnetic field and what is magnetic flux, because there are two different terms that always look alike and must involve each other, but when you write down the answers, please make sure you use the correct terms. Okay, magnetic fields inside the area is called magnetic flux. So we are actually using magnetic flux, the change in magnetic flux. Okay, the change in magnetic flux, because we want to know what is the flux final minus flux initial, in order for us to understand that this, okay, flux final minus flux initial can be or can contribute to the can contribute to the induced current. Okay, contribute to the induced current. So we will see afterwards how can we get the Faraday's laws of inductions. Okay, so these are the Faraday's laws of induction. Okay, so what is Faraday's laws of induction? Faraday's laws, and EMF is induced only when the magnetic flux through a loop changes with time. Okay, Faraday's laws and EMF is induced only when the magnetic flux through the loop changes with time. So, in the Faraday's laws of induction, it doesn't involve induced current. Remember, okay, but okay, They want you to understand that induced current can be derived from the induced EMF. That's why they are mentioning about induced EMF. So these are induced EMF. Sometimes they use the symbol like epsilon, but you can also use V. Okay, but never mind, that doesn't involve much, but you need to know that this either EMF or V, they are using the same unit, which is volt. Okay, so EMF equivalent to negative N, okay, delta flux over delta time, delta flux over delta time. Okay, N is what? N is the number of loop. Okay, number of loop or number of turn of the wires. Okay, and delta flux is what? Delta flux is the flux initial minus flux final, or T final minus T initial. So that is the how we can interpret the delta. Okay, final minus initial. And what happened to the negative sign? Okay, negative signs indicates that the induced EMF opposes the change in the magnetic flux. Yes, that means if you want to make the induced EMF greater, so you need to do some negative sign. It's like equivalent to the one that we use to do in F equals to Kx. Okay, negative Kx. So negative means, okay, um, a restoring force. Okay, restoring force, that means the force, when we try to bring the force to the right, okay, uh, the spring uh, will have to go to the left. Okay, it wants to always opposing the directions of motion, but in this case, okay, it always oppose the change in the magnetic flux. So what is the change in the magnetic flux all about? Okay, let's say if the magnetic flux is changing bigger, okay, increasing, so it doesn't want to increase. So it want to reduce back to decrease. But when we decrease the magnetic flux, okay, occasionally you have to make it change in order to induce the EMF so that the flux should be increased back. And after it increase back, you should always turn back to the decrease position. Okay, it must always decrease. So that's how the negative sign is all about. So the induced EMF must always oppose, okay, melawan arah change in magnetic flux. You cannot have the same magnetic flux, okay, because the magnetic flux should change at a time. Okay, the magnetic flux should always change as a function of time. So that is all about Faraday's laws of induction. So how can we see that thing? Okay, either the value is positive or negative, but normally when we calculated a magnitude of induced EMF, okay, we often doesn't bother about the negative part. Okay, in fact, in at the delta phi over delta t, or delta flux over delta t, we can also put the modulus. Okay, because in the magnitude part doesn't matter, we should calculate it, okay, as it is. So the value should always be positive. Okay, but if you want to look at, well, you want to look further, what is negative all about in the negative sign all about in the induced EMF, I'll show you later in the process of Lenz law, because the negative part in the Faraday's laws of induction can be explained using Lenz law. Okay, Lenz law afterwards. Okay, I'll show you the Lenz law. Okay, so let's do some examples. So the induced EMF in a single loop of wire has a magnitude of 1.48 V. So this one should be EMF. Okay, when the magnetic flux is changed from 0.854 850 Tesla meter square. So this should be flux. Okay, and also this one is in initial to 0.11. So this one is final. How much time is required for this change in flux? So you can see EMF equivalent to N, okay, delta flux over delta time. So a single loop means one, doesn't matter. So what is delta flux? Okay, so this one is 1.48 volts. Okay, so ingat delta the 5 final minus initial over time. So you can have 0.85 minus or 0.11 minus 0.85, but if the modulus times t, so t can bring here, so 0.11 minus 0.85 modulus divide by 1.48. So that will give you answers. Okay, uh, you can calculate it by yourself. Okay, what is the final answers, right? And the value should always be positive as we want to measure the time. Okay, so let's look at another examples. A bar magnet is moved rapidly. Okay, to move rapidly means it's always moving. Okay, towards a 40-turn circular coil. 40 turns means an circular coil. Remember when we want to calculate A, okay, circular. As the magnet move, the average value of B cos theta over the area of the coil increases from 0.0125 Tesla to 0.45. Okay, remember, okay, B initial is 0.0125, B final is 0.45 Tesla. Okay, it's not a Tesla meter square. That means it is not a flux, but it is a B magnetic field. Okay, in time equals to 0.25 seconds. If the radius of the coil is 3.05, this should be the R. Okay, why we need R? Because we want to do pi R squared. But remember to do it in the SI unit. Okay, and the resistance of the wire is 3.55 ohm. So this should be the R. Find the magnitude of number one is A, induced EMF. So what is induced EMF? They want to know what is induced EMF. And number two is induced current. Okay, so first of all, you need to remember about Ohm's law. Ohm's law, V equals to IR. So in this case, EMF equals to IR. So induced EMF equivalent to induced current times R. Look at how they evolve now. Okay, induced EMF, induced current will fall on the same V equals to IR. Okay, if you have induced EMF, then after and then that will be the induced current. So when you calculate at part A induced EMF and then you divide it with resistance R, then you can have induced EMF on part B. Simple. Okay, so now let's look at what we should do on the induced EMF to calculate the induced EMF. First of all, okay, you need to calculate the phi, okay, or magnetic flux. Magnetic flux is, okay, here B1 or B initial 0.0125 times with the area. Area we need to calculate pi r, and this is r. This is pi, this is square, so pi r square. So then you can get 3.65 10 power of negative 5 Tesla meter square or Weber. And then on the final part, we'll have a magnetic field final that is 0.45 times pi r square, the same area. Okay, in the end, you can get 1.32 10 power of negative 3 Tesla meter square. And then you bring into this equation, okay, EMF equals to N delta phi over delta T. So delta means a 40-turn coil. Remember to put 40 at N. Okay, and then 1.32 times 10 power of negative 3, okay, Tesla meter square minus with 3.65 times 10 power of negative 5 Tesla meter square. Okay, divide with the 0.250 seconds. Okay, times with 40, then you can get 0.205. Remember, okay, if the answer is negative, okay, just put it positive because everything that we calculated earlier is in the modulus. Okay, is in the modulus. right? From 0.2, so this should be the induced EMF, and induced current, okay, induced current is equivalent to induced EMF over R. So what is induced EMF? 0.205 divided with 3.55 ohm. So the answer should be 0.0577 ampere, right here. Okay, it's very straightforward in terms of calculations. Okay, so that's how they determine the flux, or they determine the magnetic fields using the first question that we are. It is, or it involves straight away the flux. Okay, but in this question, okay, in this the second examples, okay, it doesn't involve any flux. Okay, because it comes from the same area, but the difference in the magnetic fields. Okay, difference in the magnetic field. So we can put inside the equation. So you need to define what is the change in flux. So calculate separately between flux initial and flux final. Okay, with that, I'll stop here. Okay, and we'll take a break for a few minutes, and then I'll start with the Lenz law afterwards. Okay, so if you have a question, just put in the chat box. Okay, so let's continue. But before we continue, I would like to play some video in order for you to understand what is Lenz law all about in terms of to imagine or how to get the right concepts of Lenz law. Okay, maybe we try to do it a different way because Lenz law needs you to understand the concepts of the magnetic fields and also magnetic flux. Okay, so I'll play the video.
I'm going to give you two versions of Lenz's law, and then I'm going to show you many examples of it. Okay, so for Lenz's law, the direction of the induced current will be to minimize the change in magnetic flux. Okay, so you use Lenz's law to find the direction of the induced current, and the direction is always going to be to minimize the change in magnetic flux. Okay, that just makes sense, and I'll tell you why in a moment. Here's another way of looking at it. This is kind of a personification. You know how we personify electrons wanting to get away from other electrons when really they don't really want to get away from them. We don't think, at least. But in any case, the personification of Lenz's law goes like this. Just as mass resists changes in its velocity, that's sometimes called inertia, that the fact that mass resists changes in velocity, it doesn't mind velocity. Mass doesn't mind velocity. What it does mind is changes in its velocity. It resists changes in its velocity. Well, so same with conducting hoops. They resist changes in the magnetic flux inside them. They want they're like the ultra conservative as far as magnetic flux is concerned. They don't want the magnetic flux to change inside them. And if it does, they're going to create a current in themselves that will minimize the change in flux. Okay? Now that kind of makes sense because could you imagine if we had a wire that had, let's say here's a circular loop of wire. This isn't a circle. This is the wires right here. This is air inside here. And imagine I had X's. Okay, so we got this magnetic field. And once again, the only magnetic field that matters is the stuff that's enclosed that's actually going through the hoop. Not enclosed, but is going through the hoop. And could you imagine when this if this all of a sudden started to grow, if the X's started to grow, then what would happen is, what would happen if the current then started to be induced in here, excuse me, in such a way as to get the current to grow more, or the field to grow more. So like you induced a current in here so that that current itself made more X's, which would then induce more current, which would make more X's, which would make more current, which would make more X's. And so there's a conservation of energy thing going here, whereas it would be weird if all you had to do was increase the field a little bit, and then all of a sudden there'd just be this great big field in here, always growing, growing, growing. Like, where's all that energy coming from? Well, in fact, it doesn't work that way. What it does is it minimizes the change in flux. The current, if the X's are growing, the current will go the other way. So I want to tell you how that works. Before we do that, let's just talk about hoops for a second. I am going to be coughing a little bit in here because I have a little bit of a cold here. But if we have a hoop, and if the current in this hoop is going that way, let's just agree on something here. If the current is going this way, then there's two ways to find the field that's enclosed in this hoop that's due to this current. One way is to put my thumb in this direction and curl my fingers. When I curl my fingers, that means that in the hoop, there's a field going out at you guys. Okay? That's one way to get that. So when current goes this way, there's a magnetic field going that way. Now outside, it's going to be down. But you know what? For all this, everything we're doing, it's only the inside that matters. Okay. If it's going the other way, then it's going to be If the current's going this way, then the field will be down. There's another way to get this, though, and that is that you could use another right-hand rule where you curl your fingers in the direction of the current. So if the current's going this way, you can curl your fingers and the direction of the current will be out at you again. And it's that rule that I'm going to use a lot in these, okay? I'm going to go with this second one. So my fingers are going to be the flow of current, and my thumb will be the direction of the field inside the coil. Okay, so let's take a look. So let's say that we have a magnetic field. I'll put the magnetic fields in red. So let's say we have a magnetic field, and let's say there's X's here, and it's going like that. X's. And the X's are increasing. So if the X's are increasing, then this is not going to be happy, to personify this again. And it doesn't care about these outside ones, but the inside ones, it's going to try and stop them from increasing by making its own field that is dots. So the field's going in, so it's going to try and make its own field out. To make its own field out, that means the current is going to go this way. That's the direction of the current. That will give you a field out that will try and slow this field from increasing. Okay, let's do that with dots this time. So we got a bunch of dots. Now if the dots are increasing, then this is going to try and make X's because it doesn't want the field to change. And so it's not just, if I didn't tell you that it was increasing or decreasing, you wouldn't know what's happening in here. In fact, if there's just B and it's not changing at all, it's perfectly happy. But as soon as I tell you that it's increasing, then it's going to try and make X's. To make X's, it's going to go this way. That's Lenz's law. Excuse me. Next one. Let's have this be X's. And now it's decreasing. So the fact that the X's are decreasing inside, it only cares about inside, then it's going to try and make dots. And so to make dots, it's going to go this way. Oh, I must have got that wrong. If it's to make dots, did I get this one wrong? The B is increasing, so it's going to try, oh, I'm sorry, B is decreasing here. So B is decreasing, and so I'm sorry, I was going to mess you up there. Because B is decreasing, these X's are decreasing, it's going to try and make its own X's this time. So it's going to try and make its own X's, and so to make its own X's, it's going to go the other way. My apologies. Hope you didn't stop that short. See how that makes its own X's now? Why does it want to make X's? Because these X's are disappearing. Come on over here with me. Now let's put some dots in here. That means the field is coming toward us. So now it's going to try, and the B's are decreasing, so it's going to try and make its own field that's coming out. And to make a field that's coming out, it's going to go this way. See how that makes a field coming out? Okay, let's move on over to here. Now we have a current in this wire. Because of that, we have some field here. Now the I is increasing in the wire. So which way will the field be induced in this hoop of wire? This is a hoop of wire. Okay, well if I is increasing, then I'm thinking that there are X's here. Now they're strong here, and they drop off here. They're not as strong out there, but there are X's, and if I is increasing, those X's are getting bigger. And so it's going to try, it doesn't want the X's to get bigger. And so it's going to try and negate that effect by making its own dots. And to make its own dots, it's going to make the current go this way. Yes, dots. Last one for this video. Okay, now if I is decreasing, let's see, we have a field that's going into the page still. So these are X's. but they drop off as you go out. Now the I is decreasing, so that means that these X's are going down, 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 down. And so if they're going down, 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 it's going to try and make its own X's. To make its own X's, it's going to go the other way. You see how Lenz's law works? It's always trying to keep the status quo. So if the X's are increasing, then it will try and make dots. But if the X's are decreasing, it will try and make X's. Okay, thanks. Bye.
Okay, so that is Lenz law. All right, so Lenz law is always opposing. So let's look at first. Sorry. Okay, can you see the page here? All right. So now we have a Lenz law situations. Now we have a certain current, okay, a loop, a certain loop, certain loops that I give on the top figure, okay, on your left hand side, top is A, okay, that B increasing A, and then afterwards is on your top right is B increasing, so that is B, and afterwards on the middle left is B decreasing, so that is C, and B decreasing on the right middle right is D, A B C D. Okay, so the Lenz law needs you to get the directions of induced current. Okay, in order to get the directions of induced current, you need to understand that what is happening to the magnetic field. Okay, it's either magnetic field is increasing or decreasing. So that depends on the situation. So let's say, okay, that particular loop. Okay, let's look at the particular loop. Okay, on figure A first. Okay, on figure A, okay, now we can see that on figure A, B is increasing. When B is increasing inside that loop, okay, inside that loop. Nah, di dalam bulatan tu, bilangan X semakin bertambah. Bila bilangan X semakin bertambah, apa yang berlaku? Dia mesti nak kurangkan balik. Okay, it's always opposing the number of the magnetic flux. Always oppose the change in magnetic flux. Ingat, okay, Lenz law or Faraday's laws of induction will tell you about, okay, the induced current is is created by opposing the number of magnetic flux, okay, in the circular loop. Okay, so cerita dia ataupun circular in the loop lah, in the circle of loop. So dalam figure A, okay, if you can see the figure A right now, you have three axes. 3x. X means magnetic field going into the page. Okay, magnetic field going into the page. So bila dia kata magnetic field increase, so what is Lenz law will say? Lenz law, okay, is always opposing. Okay, opposing the number of magnetic flux. So what happened is they want to make that we should make the other way around. So instead of kita tambah X, so kita terpaksa kurangkan sebab dia dah increase. Bilangan X increase, so we want to reduce back the bilangan X. So macam mana nak reducekan dia? Kita terpaksa buat benda yang berlawanan arah. Apa berlawanan arah dia? So kalau dia masuk ke dalam, so kita terpaksa buat dia keluar. Macam mana nak buat dia keluar? Now you point your fingers to the screen. You point your fingers lagi, guna right hand rule. You need to use your right hand rule. So your thumb should be the directions of where you should point the magnetic field to oppose the increase of magnetic field. Okay, where you should point your fingers. So this thumb should always pointing to yourself, pointing to yourself, and then you can see that you curl your fingers around the screen, And now you can see that the curling of your fingers is actually going to the position of counterclockwise, because you want to make sure that the current that you are creating in the induced current should always oppose the number of magnetic field inside the loop. Okay, so inside the loop ada 3, so kita nak oppose dia sebab dia semakin banyak kan, daripada 3 dia jadi 4, 5, 6, so kita nak reducekan dia. So how to reduce it? We need to point our fingers, point our thumb to ourselves. Okay, considering you are semua duduk tengok pada screen ya. Okay, point your fingers to yourself right now, because you want to make sure that you cannot have any more X. X kita tak nak dah, kita kena buat dia dot. So macam mana buat dot? Tangan awak ke arah awak diri awak sendiri. Okay, point to yourself and then curl your fingers. Awak akan nampak you curl your fingers to the counterclockwise. So that is the directions of the induced current in figure A. So in figure B is also the same. Okay, but magnetic field is increasing. Okay, but dalam keadaan macam mana? Keadaan magnetic field dia keluar daripada page. So apa yang kita nak buat untuk oppose dia? Kita terpaksa buat. Now you point your thumb towards the screen, and then you curl your fingers. So that's how you can get the induced currents direction. The directions of induced current. Okay, so every time you see the problem, always look at the perspective of this. The B now is increasing or decreasing. If it increase, now you want to make sure it decrease back. So that's why I'm telling you the Faraday's laws of induction always make a point that it's always oppose the change in the magnetic flux. So in this case, they're telling you about magnetic field, but it's just the same, because magnetic field inside the loop is called as magnetic flux. So B ataupun flux doesn't matter. Okay, as long as awak faham flux itu datang daripada B juga. Alright, so let's lay at the middle figure. Okay, middle figures. Look at the middle figure. Look at the figure C. Okay, magnetic field is decreasing. Okay, up. Okay. What can we do to bila dia decrease, kita nak top up balik. Nak top up jenis macam mana? Nak top up jenis yang masuk ke dalam. So masuk ke dalam, now you point your thumb towards the screen and then you curl your fingers. Curl your fingers to the clockwise position. So that's why tadi pada mula-mula masa dia explain tadi salah kan? Sebab dia confused. Lepas tu dia betulkan balik, dia mesti dapat clockwise position untuk dapatkan balik, untuk increasekan balik magnetic field inside the loop. Okay, so untuk figure D, cuba tengok macam mana dia buat. Okay, figure D, dia akan dapat magnetic field, induced current dia ke arah counterclockwise. Why? Sebab dia masih decrease. So bila decrease, dia nak tambah. So now you point your fingers to yourself, sebab dia nak tambah balik. Bila dia kurang, dia nak tambah balik. Tapi kalau dia banyak, dia nak kena lawan dengan arah yang bertentangan. Simple. Okay, have to make the same situation ni again and again. Whenever you have a decrease, look at what is the type of the magnetic fields. It's either going into or going out of the page. That depends on the situation. Okay, depends on the situation. So in this case, you need to do some logic thinking of when a decrease in the magnetic field, then you need to add up the same types of magnetic field. But if there is an increase in the magnetic field, then you need to do, we need to oppose that increase so that you will have a stable value. So that you will always oppose, so it will go decrease back. Okay. So this is very good examples on how to determine the induced current. Okay. So let me stop this one first. So that will be the Lenz law. Okay. And then we go to the motional EMF. Okay, motional EMF. So here we see a metal rod that is free to move in the vertical direction here. Okay, this is the metal rod. Wait. Okay, this is a metal rod, right? Okay, so the metal rod is free to move. Okay, free to move in the vertical directions. Okay, so what happened is now you look at the magnetic fields around the circular loop. So this is a circle. Yes, this is the loop that we are talking now. Now you have at least almost about 8 magnetic field. Okay, 8 numbers of magnetic field. Okay, 1, 2, 3, 4, 5, 6, 7, 8. You have almost 8. Okay, 7 and 8. Okay, you have almost 8 magnetic field inside the loop. What happened if the metal rod now reduced to this part? Okay, it's going down until this part. What happened to the magnetic field inside the loop? So magnetic field inside the loop now becomes 6. So it decreasing. So what happened if the magnetic field is decreasing? Okay, when the magnetic field is decreasing, they want to oppose that decrease. So we want to add again. Okay, add up. Okay, add up the magnetic field inside the inside this ni. So daripada 5 nak tambah balik jadi 8. So how to do that? So we need to add the same type of loop. So same type, kita gunakan right hand rule macam saya cakap tadi, simple. Now you put your fingers at your screen. Okay, your thumb should be directs towards you. Okay, your thumbs menghadap awak. So you curl your fingers, and then you can see that. Okay, the magnetic field now have been increased back. So the directions of the induced current in this loop is considered to be that way. Okay, this way, this way, this way, counterclockwise. So to oppose the decrease in flux, Lenz law implies that the induced current must flow in the direction that strengthen the magnetic field. The directions of current is counterclockwise. Okay, counterclockwise. So that's how very important to understand the Lenz law in order to get the directions of the induced current. Okay, Lenz law is how the method or how to measure or how to determine the directions of the induced current. Simple. Okay, because when current being induced in the loop, so you need to know which directions of the induced current. Okay, so it's very good to understand that. So the force due to the induced current is upwards, and it is slowing the fall. So this is the method of what we have been telling you just now. Okay. Okay, so in order to do that, you can check back what happens. Okay, when you have a current being clockwise, counterclockwise. So we have a counterclockwise. Now you use a right hand rule, so you will have a force going up here. Okay, because should be your hand. Okay, and that should be your thumb. Okay, this is your thumb. So this is the directions of current, and it will reflect back, or you will go your right hand rule, rest of your hands, okay, go to the out of the page, and then it will go upwards. So we are saying that the induced current is upward and will slow down the fall of the metal. Okay, it will slow down the fall of the metal. It's very good to understand the And then afterwards, if what we call as mechanical work and electrical energy. Okay, the mechanical work and the electrical energy, which means we learn the motional EMF. So how to do a motional EMF? So this diagram shows the variable we need to calculate the induced EMF. We have R. Okay, now we have V. Okay, we have current. We have I. Okay, it's going uh, uh, what I should say as clockwise position. Okay, current in the clockwise position. And what happened if we try to bring this metal rod? So again, this is metal rod. Okay, we try to bring from this position, okay, position A to position B. Okay, this metal rod, and we try to bring it from point A to point B. Right? So in the point A and point B, so there are a certain area. So the change in area. Okay, if we try to bring a V to A, from A to point B, what happened if, okay, so first of all, you need to know the directions of the magnetic force, okay, directions of the magnetic force due to the current carrying wire, so this current, and of course the magnetic force from the right hand rule is going to the this part. So when you have, so it's trying to slow down. Okay, it's trying to go to this part. Okay, so we need some external force. Okay, we need some external force to balance the magnetic force. So in this case, we need to support this. In order for the magnetic force trying to pull this metal rod, okay, towards the bulb, okay, towards the bulb. So we need to do some external force, okay, to make sure it will balance. Okay, it will balance. So in order to do that, we must always make the change in flux. Okay, because the change in flux, okay, we can make the bulb because of the change of flux. Okay, change of flux. So we can gather the induced current. We can create the induced current, okay, by changing the flux. And of course, so for the induced EMF, so we can make sure like this. Okay, so change of flux is B times A. Okay, B times delta A, because the delta, this, let's say this is A and this is delta A. Okay, so A initial now have been different area. So we can say that the area is come with the V delta T times with L. Okay, B VL, okay, VL times delta T. VL times delta T is considered to be A. Okay, VL delta T is considered to be A area. So from EMF, induced EMF equals to N delta flux over delta T. So we can make sure that delta flux is BVL delta T. So you can easily, okay, cancel out delta T in order to get BVL. So what is BVL? In this case, okay, BVL, B stands for magnetic field, V is the velocity, and L is the length. Okay, L is the length between the wires. Okay, so in this case, we can have E equivalent to BV, and of course, we can derive that, okay, ILB. So in the end, we can have F equivalent to B square VL square over R. Okay, BV L square over R. So, and the mechanical power, so we can have P equals to FV, P equals to FV. And for the electrical power, P equals to I square R. Okay, because when now we have I, okay, remember, I is what? I is um, here, BVL over R. Okay, current I is BVL over R. Okay, BVL over R, because this is induced EMF. Okay, remember reduced EMF I equals to R. So this is induced, this is induced. So induced current is induced EMF over R. So what is induced EMF? BVL over R. So that's how we get here induced current, okay, BVL over R. So we can put it inside here, okay, in order to get the same power. Okay, you can look here as in the mechanical part, the power is B square V square L square over R, but the electrical power also give you B square V square L square over R. So this is how, just to show you the mechanical and the electrical is just the same when it comes to the induced current. So the mechanical power has been converted directly into the electrical power. So we have to make sure that we can assure that the mechanical power, mechanical means what? This one. Okay, we try to bring this metal rod to this part. Okay, from point A to point B. So we do a mechanical work in order to get the electrical energy. Simple. Mechanical energy converted to electrical energy. So that's how we determine. Okay, so let's look at these examples. Okay, the light bulb in the circuit shown here has a resistance of 12 ohms. So this is R, and consumes 5 watt, which is power. The rod is 1.25 meter. This is L, and move to the left with a constant speed of. So this is V. What is the strength of the magnetic field? So you want to know what is B. And B, what external force is required to maintain the rod's constant speed. Okay, so how to do that? First of all, okay, you can establish first. You want to calculate the strength of the magnetic field using these equations. Okay, because P is BVL square over R. P is B square V square L square over R. So you need to what? B. Okay, so you can define that B is 2 Tesla, and then using the second part, okay, we can also derive that F equals to B square VL square over R. Okay, so to do that, okay, we can find that the power divided with the velocity is equivalent to 1.6 Newton. Or maybe you can use a simple one, that B equals to FV, or maybe you can use the B square VL square over R, right here. Okay, it's up to you to use because the answer is the same, 1.6 Newton, 1.6 Newton. Okay, so in this part of the story, this part of the chapter wants you to do a mechanical work in order to get the electrical energy. Okay, these are the applications of the induced EMF, generators and also motors. Okay, so you can know what is generators. When you use the generators, for those who have been a generator, you know what is all about when it comes to the generating the electrical energy. So it's converting mechanical energy into the electrical energy. Okay, so this one you should know, at least you know what is the applications of the induced current. Okay, so let's look at these examples. The coil in an electric generator has 100 turns. So this is N, and area. Okay, this is desired that the maximum EMF of the coil is EMF when it rotates at the rate of 60 cycles per second. Okay, 60 cycles per second. What is the angular speeds of the generators? Okay, this question involve omega because it involve angular speeds. Okay, so at least at this part you need to know what is the generators, but I don't think that the question that will come out in the final will ask you about some things that you learned in the previous semesters. Okay, because the angular speed we learned in the semester 1. Okay, but at least try to imagine, try to get to know the application is generators and motors. Okay. Okay, this is how the mechanical works in the generators. Okay, so we do. Okay, macam kita tengok machine kan, it's starting with the mechanical output. Okay, sebab tu kita tarik dengan tali, kan, tarik dengan tali. So it will generate here, okay, induce some current. Okay, when there are some change in the magnetic field, so you can see here, this is north and south, and in between there are magnetic field. So when the loop is changing, what happen is it can induce a current inside the loop. So therefore, you can have an electrical output. So that's how you can turn from mechanical energy to the electrical energy, or vice versa, from the electrical energy to get the mechanical output. This also can. So right now we want to learn about inductance. Okay. When the switch is closed in the circuit, a current is established that increases with time. Okay. What type of circuit? Here. Right. So inductance. Okay. The directions of induced EMF is given by the Lenz law. Okay, look here. Now we have EMF, okay, we have R, and we have L. So this is the inductance, L. Okay, before this we have R, we have capacitor, now we have L, inductor. What is the purpose of inductors? To get the magnetic field inside the particular circuit. Okay, so that's how we did it using the inductors. Okay, the inductance in the proportionally constant that tells us how much EMF will be induced for a given rate of change in current. So EMF is equivalent to N delta flux over delta T. So this should be the Faraday's laws of induction. That is equivalent to, now EMF is also equivalent to L delta I over delta T. So remember, EMF is equals to N delta flux over delta T, and EMF also equivalent to L delta I over delta T. Delta I use D. So L is inductance, N is the number of loops. So we can join this equation to get L equals to N delta flux over delta I. Okay, L equals to N delta flux over delta I. That means we cancel out T and delta T from both sides. So we can have delta flux over delta I. Okay, given the definitions of inductance, the inductance of a solenoid can be calculated using here. Okay, L equals to mu naught N square over L N square over L times E. Okay, remember N is the number of loop, L is the length of the solenoid. Length of the solenoid times A is the area of the solenoid, which will bring us to this part. Okay, to this part. Okay, let's lay again. Look at the example. Look at the equations. Okay, mu naught N square AL. Mu naught N square AL. Okay, remember, N is the number of loop. Okay, number of loop. When used in a circuit such as solenoid is called inductor. So maybe you can call it as inductor. So that's why we are calling inductance of a solenoid. Because the solenoid will give you a current, okay, and generate a magnetic field so that you can calculate its inductance. Okay, now we may take a look at these examples. When a 500 turn solenoid, a 500 turn solenoid is 8 centimeters long, so this should be N and this should be L. Okay, when a current, okay, please remember to differentiate between this L and L because this is in inductance. Don't simply use a capital L. And this is length of solenoid. Okay, when the current in this solenoid is increased from 0 to 2.5, it's from 0 to 2.5, so this should be delta I. In 0.3 seconds, this should be T. The magnitude of the induced EMF is, so this is induced EMF. Find A, the inductance. Okay, find A, the inductance. So L equals to delta, EMF equals to L delta I over delta T, if I'm not mistaken. Sorry, delta I over delta T. Okay, delta I over delta T. So in order to get L, L is equivalent to epsilon naught or induced EMF delta T over delta I. Okay, delta T over delta I. So what is delta T? Uh, right? So induced EMF delta T over delta I, 2.5 divided with 0.35 seconds. So in the end, you will get 1.7 milli H. Okay, the unit for inductance is H, stands for Henry. Henry. Okay, the unit for inductance is H, stands for Henry. Capital H, okay, capital H. Right? So in this case, we get 1.7 millihenry. Okay, and that from that particular value, you can calculate the second one, the cross-sectional area of the solenoid. That means if you look at this part, the cross-sectional area, okay, you can determine the cross-sectional area of the solenoid using these equations. Okay, when you have inductance, so you can find what is A. So use this equation in order to get the solenoid. So in the end, we look at area equivalent to 4.3 times 10 to the power of negative 4 meter square. Okay, so that is how you involve the inductance in the solenoid. Okay, remember inductance have the unit Henry. Okay, Henry. Okay, now we have okay, we go to the RL circuits. Okay, the RL circuit stands for, okay, resistors and inductor. Before this, we learned about RC circuit. Okay, RC circuit. RC circuits mean resistors and capacitor. But RL stands for resistance and inductance. That means in the circuit, in the direct current circuit, we'll have R and also L. So now we can establish this equation I. Okay, when the switch is closed, the current immediately start to increase. The back EMF is in inductor is large, the current changing rapidly. As the time goes on, the current increases more slowly, and the potential difference across the inductor decreases. Okay, potential difference across the inductor decreases. Therefore, the most important thing when you have RC or RL, remember RC will have a time constant tau equals to RC, but in here we have RL, so tau will be equivalent to L over R. L over R. Okay, the time constant for RL circuit is L over R. This is the time constant. Okay, so at least you know what is the time constant when it comes to the RL circuit. The most important thing at RC and RL circuits, for the direct circuits, you need to know the time constant. Okay, remember this word, time constant. For the RC is torque equals to RC, and for RL, torque equals to L over R. Tau, not stop. Tau. Okay, this is not T. I always heard the student used to say as T. It's not T. It's tau. It's tau. And then the last part of the energy stored in the magnetic field is which means the energy stored in an inductor using, okay, U equals to half Li square. Half Li square. L is the inductance and I is the current. Okay, and half Li square, I square, that means you have joule. The unit for energy stored in the inductor is joule. So work is required to establish a current in an inductor. It takes energy to establish a current in an inductor. This energy is stored in the inductor's magnetic field, which means the capacitor. Let's say the capacitor storing in E, electric field, but inductor, it will store the energy, will be stored in the magnetic field. So considering the EMF needed to establish a particular current, so this is what we call as induced current. The power involved we find is U equals to half Li square, right? U equals to half Li square, and the inductance. So now the last part of the energy storage is U equals to Li square. So when U equals to Li square, so the inductance of the solenoid, therefore the magnetic energy stored in the solenoid by combining inductance of the solenoid here and the magnetic fields of the solenoid. This one we learned in the previous semester, previous chapter, okay, previous chapter. So we can combine these things, right? So inductance of the solenoid is L equals to mu naught, okay, N square over L times A. Okay, and also the L half Li square for the energy store. So we can bring out to half mu naught B square A L. So the energy stored in the inductors can be also write down as half mu naught B square AL. Okay, doesn't matter, this all will be in the appendix, but you need to know how to use these equations. Okay, how to use these equations, it's much more important. But normally just use half Li square. Half Li square will be used regularly. Okay, so okay, look at the transformers. I think most of you are already um, familiar with the transformers because we used to calculate it in the secondary school. Transformers involve primary and secondary circuit. Why we put transformers in here? Okay, if you notice here, this is the AC circuit. What means that AC is the alternate current circuit. But right now we are actually uh, learning about um, learning about direct current circuits. But the transformers will be a good applications. How can we describe the primary and also secondary circuit? Okay, this is the primary circuit. We have VP and NP, and on the secondary circuit we also have NS and VS. And N is stands for number of turns of the wire, and V is velocity or potential difference, doesn't matter. P and S, P is primary and S is secondary. Okay, and you need to remember one thing. Okay, in order to understand the transformers equation, try to remember power. Power equals to IV. Okay, power equals to IV. So P primary will be equals to P secondary. So IP VP equals to IS VS. Okay, we make it simple like this. Okay, and then if you want to know what is VP, so VP over VS will be equivalent to IS over IP. And how come is the number? Number is considering here NP over NS. So these are the how we can connect between number of loop, voltage, and current. Because in the transformers, yeah, always okay, want to know the number of loop, voltage, and also current. It will involve between these three, and of course the power. Okay, so these are the things that you need to know. Okay, and IS at the top, VP at the top, so IP at the bottom, VS at the bottom, but NP will follow V. So primary will be at top, and S will be the denominator. Okay, so use the power. Power P primary equals to power secondary. Again, IP VP equals to IS VS. Okay, and then you can VP bring out VS over here. VS equals to IS over IP. Remember, VP and VS look will be okay like that. But N will follow VP. NP over NS. Simple. Okay, right. So these are the examples, the last examples of uh, the transformers. Okay, a common summertime sound in many backyards is the zap heard when an unfortunate insect flies into a high voltage bug zapper. Okay, typically such device operate with a voltage of about 4,000 volts obtained from a transformer plugged into a standard 120 volt outlet. Okay, so these are the 120 volts. So it will give you VP about 4,000 volts. How many turns are on the secondary coil of the transformer if the primary is 27? So NP is 27, and you want to know what is NS. Simple, eh? NS is 900 turns. Okay, you can use the formula that I give you just now about considering voltage and current. So that will be the end of the topics of the Faraday's laws of experiment, okay, Faraday's laws of induction, and the magnetic flux. Do you have any questions? Ada soalan tak?
Sir, saya ada soalan.